Here's the circulation curl version of Green's theorem. Let's apply Green's theorem to this problem here. So we are being asked to compute the circulation of f is equal to sine of x comma x squared y cubed around curve C, where curve C is the border, the boundary of this triangle with this orientation. So if we want to do this straightforwardly to compute the circulation here on this side, we'd have to compute 1, 2, 3 vector line integrals. We certainly could do that, but I think this is a case where Green's theorem is going to be a very useful here. Instead of computing the circulation along the three sides, we're just going to calculate this double integral right here. So that will be very easy, because that will be a very easy region for us to integrate over. So this is our R. Okay, so what do we have to do here? We need partial n partial x minus partial n partial y. Okay, so the partial derivative of n with respect to x is going to be 2xy cubed. And then the partial derivative of m with respect to y, this right here is m. There's no y dependence at 0. So we are integrating 2xy cubed over this region right here. Now this becomes a chapter 15 problem. We need to do a double integral here. We need to integrate, let's see here, x runs from 0 to 2. And then for a particular value x, y runs from 0 to x. So these are our bounds here of the integral. And then our integrand is 2xy cubed dy dx. Okay, antiderivative with respect to y will be xy to the 4th over 2. Plug in y from 0 to x. And we would end up with integral x from 0 to 2 of, let's see, so plugging in y is equal to 0 just gives us 0. Plugging in y is equal to x would give us x to the 5th over 2 dx. And an antiderivative of this would be x to the 6th over 12. And plug in x from 0 to 2. And so we get 2 to the 6th over 12. So hopefully we can agree here that instead of doing 1, 2, 3 vector line integrals where you have to parameterize each one of those, this is a lot easier calculation. It becomes a pretty easy chapter 15 problem thanks to the circulation curl version of Green's theorem.